In this video, I will give an introduction to ABC post-sampling adjustments, and in particular ABC-GLM. Let us begin by briefly reviewing the most basic ABC algorithm, the ABC rejection algorithm. The ABC rejection algorithm proceeds in the following steps. In the first step, we sample a candidate parameter vector θ' from the prior distribution. In the second step, we generate some simulations d' using that candidate vector θ' as parameters. In the third step, we then summarize the resulting data using some summary statistics. In the fourth step, we accept that candidate parameter vector if the simulated summary statistics S' are close to the observed summary statistics S observed. In order to evaluate if summary statistics are close, we have to use some distance metric as well as a threshold up to which we accept. Finally, we're going to repeat steps 1 through 4 until enough posterior samples were gathered. Let us next briefly illustrate this algorithm graphically. Here on the right we see two panels. On the top panel, in gray, we have the prior distribution. In the lower panel, we show simulations that were obtained. For each simulation, that is each dot, a random candidate parameter vector θ was drawn from the prior distribution. We then simulated some data d' under that parameter vector, summarized that data using summary statistics, and then placed a dot at the right position on the graph. Simulations that were considered close to the observed summary statistics are shown in blue. Here on the right, we see the threshold indicated by an arrow. These accepted simulations are now considered samples from the posterior distribution. We can plot that posterior distribution using kernel density smoothing, as is shown here on top as a blue line. It is important to note that this algorithm does not generate samples from the full posterior distribution. Instead, it samples parameter vectors for which the summary statistics were close to those observed, according to a distance metric and a threshold. Let us therefore reflect on which conditions these ABC posteriors are good approximations of the full posterior distribution. They are reasonable approximations if two things hold. First, the summary statistics chosen are actually near sufficient for the data. That is, they contain essentially all the information about the parameter that is also contained in the data. The second condition is that the threshold delta is sufficiently small. If delta is large, then candidate parameter vectors get accepted under which it would actually be impossible to obtain the observed summary statistics. However, it might still be possible to obtain summary statistics close to those observed. As a result, ABC posteriors tend to be too broad and to include parameter vectors under which it's actually impossible to obtain the observed data. Unfortunately, the choice of the threshold delta has also a massive impact on the acceptance rate of that algorithm. If a small delta is chosen, then usually the acceptance rate is very, very low, and hence the computational power required in order to obtain enough posterior samples is enormous. In practice, one is therefore often not free to actually choose the delta one likes, but forced to accept a larger delta given the computational power at hand. And this is now where ABC post-sampling adjustments come in. ABC post-sampling adjustments generally aim at correcting for large threshold delta that were used when accepting ABC samples. To do so, they rely on the assumption that the truncated model is of a simpler form and can be learned from simulations. By truncated model, we refer here to the model among just the accepted simulations, or on the right side graphically, to the likelihood function that applies only to the blue dots. Or in other words, the goal is to actually make use of the accepted simulations, so the blue dots here on the right, to fit a simple model, a simple likelihood function and a simple prior that can then be used as surrogates for the full model. Using those surrogates, the ABC posterior might then be improved. To justify this approach, let us look at the general formulation of the truncated likelihood and then later the truncated prior. Shown here is the general formulation of the truncated likelihood. The truncated likelihood builds naturally from the full likelihood function, the probability of the summary statistics S given θ. But we do have to take care of the fact that we do truncation. That is, we only accept some simulations while others are rejected. Here, This is taken care of by this indicator function that just indicates whether the summary statistics vector concerned is actually within what we denote as the delta ball around S observed. In the one-dimensional case shown here on the right, the delta ball simply corresponds to the area close to S observed within which we are accepting simulations. Thus, for a summary statistics vector outside the delta ball, that is a summary statistics vector not accepted, the truncated likelihood simply becomes 0. For a summary statistics vector inside the delta ball, that is a summary statistics vector that would have been accepted, the truncated likelihood is simply proportional to the full likelihood. It is proportional because of truncation, so we have to divide the likelihood by the integral of the likelihood across the entire ball. Truncation also affects the prior distribution. An easy way to see that is by considering a parameter vector zeta under which it's actually impossible to generate summary statistics within the delta ball. Such a parameter vector might have a prior density larger than 0, but after truncation, its prior density is 0. It is not represented among the accepted simulations. That implies that in order to calculate the truncated prior distribution, we have to use the full prior distribution, but weight the density for every parameter vector by the probability that summary statistics obtained under that parameter vector actually fall within the delta ball. This is indicated here by this integral across the delta ball of the likelihood for that particular parameter vector zeta. Obviously, we then have to renormalize to ensure that the truncated prior distribution is a proper probability distribution. Renormalization is achieved by simply integrating the denominator across the entire parameter range. Let us next reflect upon how the truncated posterior distribution for S observed might look like. The truncated posterior distribution is simply the probability distribution of the parameter vector zeta given the observed summary statistics. It must be proportional to the product of the truncated likelihood times the truncated prior. Let us next plug in for these two terms the general solutions we found before. On the left side here, we have the truncated likelihood, which is then multiplied with the term on the right side, the truncated prior. These terms can be much simplified. A first thing to notice, for instance, is that the denominator in the likelihood, that is the integral across the delta ball of the original full likelihood, is also present in the nominator of the prior. It therefore simply cancels out. A second thing to notice is that as we are evaluating the truncated likelihood at S observed, we now have the indicator function of whether S observed is within the delta ball. Now that obviously must be the case, as the delta ball is actually centered on S observed. So this indicator function simply becomes 1, and we therefore no longer have to write it. Shown here now is a simplified version of the truncated posterior distribution. As you can see, only few terms remain. In the nominator, we just have the product of the original likelihood with the original prior. In the denominator, we have the product of these two terms across the entire parameter space as well as across the delta ball. Note that this denominator is actually a constant in this case, as it does not depend on the parameter vector zeta, which implies that the truncated posterior distribution for S observed is actually proportional to the product of the original likelihood and the original prior. And since this in turn is proportional to the full posterior distribution, it implies that the truncated posterior distribution for S observed actually matches exactly the full posterior distribution at S observed. Or in other words, if we knew the truncated likelihood and the truncated prior, we could actually obtain the full posterior distribution given the chosen summary statistics. And this really motivates this idea of ABC post-sampling adjustments. What they aim at is to actually learn the truncated likelihood and learn the truncated prior from the accepted simulations, and then to make use of those to improve the estimate of the posterior distribution. But how come we can actually learn the truncated likelihood from accepted simulations while we do not have a good formulation of the full likelihood? Remember, the reason to choose ABC methods is because the full likelihood of the model is intractable. That means we don't have any way of calculating the full likelihood distribution. The reason for why we might be able to learn the truncated likelihood from simulations, while we do not have a formulation of the full likelihood, is because we are concentrating just on the area around S observed. Indeed, the truncated likelihood only aims at explaining the relationship between parameter vectors and summary statistics at the location of S observed and a little bit around it. It is therefore a probably fair assumption that the truncated likelihood is of a much simpler form than a full likelihood that tries to explain the relationship between parameters theta and summary statistics S across the entire parameter range. We're going to next look at one particular implementation of such an ABC post-sampling adjustment, ABC-GLM, which uses, as many others do, the assumption that the relationship between parameters and statistics around S observed is actually just linear. Specifically, the ABC-GLM method assumes that the truncated likelihood is actually well characterized by a general linear model, or GLM, hence the name. Shown here is the model assumed by ABC-GLM. It assumes that the summary statistics Si observed for some parameter vector theta can actually be explained by the linear model with an intercept S0 with a matrix of constants C and an error term epsilon I. The epsilon I error term itself shall be normally distributed with mean 0 and a variance-covariance matrix sigma S. The parameters of this model, that is, the intercept S0, the matrix of constants C, and the variance-covariance matrix sigma S, are then learned from the accepted simulations, for instance using ordinary least squares. As is illustrated here on the right for a one-dimensional case, this simply amounts to actually fitting a linear regression to the accepted simulations, the blue dots in this case. The ABC-GLM method then estimates the truncated prior by using kernel density estimation across the accepted simulations. For this, a Gaussian kernel is put on every accepted simulation, and the truncated prior density for a particular vector theta is obtained as the average Gaussian density across all accepted simulations. Making use of the learned truncated likelihood and truncated prior, we can then simply build a posterior estimate by combining the two. In the top panel on the right, as a red line, the ABC-GLM posterior obtained for the particular case here is shown. As you can see, the ABC-GLM posterior is not drastically different from the ABC rejection posterior. However, it does differ in an important aspect. That is, it has a posterior density of essentially 0 for very large theta values. Large theta values may never result in actually observed summary statistics. But simulations conducted under those theta values might result in summary statistics still close to S observed. Because of the relatively large tolerance delta used, these simulations were accepted, and hence the rejection sampling posterior included large theta values. By fitting a linear model to the accepted simulations, it actually becomes obvious that these large theta values may never result in summary statistics very close to the S observed ones. But let us next quantify the improvement of ABC-GLM over ABC rejection using a more sophisticated example, but still one for which we can actually calculate the analytical true posterior so we can judge the improvement. Let us revisit the case of inferring the allele frequency f from genotypes observed for n individuals. The locus concerned shall be biallelic with two alleles, an ancestral and a derived one. And further, let the genotypes 0, 1, and 2 denote the number of derived alleles observed. The locus shall further be in Hardy-Weinberg equilibrium, such that the probability of observing a particular genotype given f is just given by binomial sampling. And finally, given f, all observed genotypes are independent, such that the probability of the full genotype vector given f is just given by the product of the probabilities of each individual genotype, given f. In order to conduct Bayesian inference, we will further assume a beta prior on f, such that the probability of a particular f is given by a beta distribution with parameters alpha and beta. Under this model, and using this prior, we can actually obtain an analytical posterior distribution. Given genotype counts n, which is just the counts of the number of homozygous ancestral, heterozygous, and homozygous derived genotypes among the n individuals, the posterior distribution is also given by a beta distribution, in this case with parameters alpha plus n1 plus 2n2 and beta plus n1 plus 2n0. We will now benefit from the fact that we have the analytical posterior distribution under this model to actually evaluate the performance of ABC algorithms. We're going to start by ABC rejection sampling posteriors and then see how we can improve them by using ABC-GLM. Shown here as a dashed line is the prior distribution on F with parameters alpha equals beta equals 0.5. Shown as a solid line and filled in gray is an example posterior distribution on some data simulated with true F equals 1/3. That data consisted of the following genotype counts: 12 homozygous ancestral genotypes, 11 heterozygous genotypes, and 2 derived homozygous genotypes. Let us next compare this analytical posterior distribution against posterior distributions obtained with ABC rejection sampling for different tolerances delta. Shown here are ABC posteriors obtained with rejection sampling by setting the tolerance delta to 0, 5, 10, and 15. In parentheses, we see the difference in acceptance rates. The delta equals 0 run had an acceptance rate of 0.5%, so a very low acceptance rate. On the other extreme, by setting delta equals 15, the acceptance rate was 52%. However, the price for a higher acceptance rate comes with actually a much broader posterior distribution. Again, looking at the extreme case of delta equals 15, the obtained posterior distribution suggests that allele frequencies larger than 0.6 and smaller than 0.1 might also be valid estimates. This contradicts the analytical posterior distribution. That implies that allele frequencies larger than 0.6 and smaller than 0.1 are no valid estimates. In fact, it seems that the observed data is incompatible with those allele frequencies. Let's next see whether we can correct for the broadness of these posteriors obtained with large tolerances by using ABC-GLM. Shown here on the right are now ABC-GLM posteriors obtained from the accepted simulations that were used on the left. In essentially all cases, the ABC-GLM posterior is much closer to the true analytical posterior distribution than the ABC rejection posteriors were. This includes the case of very large tolerances. So even for delta equals 15, we now get an almost exact match between the ABC-GLM posterior and the true analytical posterior distribution. This is obviously just an example, but before exploring the performance of ABC-GLM more generally, let us first reflect upon the conditions under which we expect ABC-GLM to work very well. There are two conditions that have to be fulfilled for ABC-GLM to be a good approximation of the true analytical posterior distribution. The first condition is that the relationship between the parameters theta and the summary statistics S is approximately linear, at least locally around S observed. It turns out that in practice, this is a very good assumption. The reason is that if we zoom in close enough to S observed, even a very complicated function tends to be linear. The second condition to be fulfilled is that sufficiently many simulations were retained such that the truncated likelihood and the truncated prior can be learned accurately. Fitting a linear model does not require an awful lot of points. However, since the truncated prior is assessed using kernel smoothing, a few thousand simulations are usually advised. But let's turn our attention now to the general problem of validating ABC inferences. Such a validation is essential. The reason is that if these assumptions are actually violated, the inferred ABC posterior might be a very bad approximation of the true posterior distribution. So far, we were mostly concerned with the fact that ABC posteriors tend to be too broad, but if, for instance, summary statistics were chosen that are not near sufficient, even wrong inference might be possible. So how do we go about validating ABC inference methods? A commonly used approach to validate ABC inferences is to actually run the inference for many simulations conducted under the model and for which the true parameters are known. Shown here are 9 example posteriors under the model we just discussed before. In each case, I first drew a random value for f from the prior distribution. I then conducted simulations under the model and given this f, and then used different methods to obtain a posterior distribution from the simulated data. In the case here, I used ABC rejection sampling and setting the tolerance delta to 0. The dashed vertical line indicates the true parameter value, so the true allele frequency used in the simulations. Visual inspection confirms that these posterior distributions are not terribly bad. At least, the true value is always contained within the posterior distribution. However, the exact position of the true value within the distribution varies a lot. In the first example up here, the true value is pretty much central in the distribution. That seems to be a common case. It is also observed here on the top right, as well as in the center. But sometimes, the true value is also in the tail of the posterior distribution. That's a case, for instance, here, where the true value is very much on the right of the distribution, or down here, where the true value is very much in the left tail. That is not necessarily something of a concern. The reason is that the true value should be in the posterior distribution according to the probability implied by that posterior distribution. So while the true value should therefore be more often close to the peak of the posterior distribution, it might sometimes indeed be in the tail. In fact, the true value should be in any integral of the posterior distribution given by the area of that integral. So in the 5% of the posterior distribution in one tail, the true value should be found in exactly 5% of the cases. We can use a very simple statistics to evaluate if that is the case. This statistics is usually referred to as the coverage property in the ABC literature. What we do is simple. For every of these simulations, we assess the position of the true value within the posterior distribution, and we do that by determining its position in the cumulative posterior distribution. That simply amounts to calculating the area of the posterior distribution on the left of the true value. So in the top left here, it would correspond to this area here. The same thing would then be repeated for every one of these posterior distributions. Since these areas correspond to the position of the true value within the cumulative posterior distribution, the distribution of these areas should actually be uniform. Shown here on the right is a histogram of this area across 1000 simulations, each conducted with a parameter value f drawn randomly from the prior distribution. As you can see, this distribution here is at least approximately uniform, and that suggests that the ABC rejection sampling posterior with delta equals 0 is a pretty good approximation of the true posterior distribution. Let's next see how the distribution of these areas would look like in case we use the larger delta. Shown here is now, as a histogram, the coverage property in case we used ABC sampling with delta equals 15. As you can see, the posterior distributions obtained with delta 15 are much broader, and as a result, the position of the true value of f is usually much more central in the distribution. In fact, it is very hard to obtain a posterior distribution in which a true value would be in the tail, simply because the posterior distributions are too broad. This is well reflected in the histogram shown on the right. You see that there is a huge peak around 0.5, suggesting that the true values are indeed very often in the center. Let us now see how ABC-GLM run on delta equals 15 simulations would actually correct for this problem. Shown in red here are the posterior distributions obtained with ABC-GLM. Similar to the example we considered before, these ABC-GLM posteriors are very close to those obtained with ABC rejection sampling at delta equals 0. So despite the very large threshold used, ABC-GLM managed to obtain posterior distributions that probably match the analytical solution relatively closely. This is also well reflected in the coverage property. The histogram shown here on the lower right actually is pretty much uniform. It is not exactly uniform. We do observe that in the very first and very large bin there is somewhat too few simulations. That suggests that the ABC-GLM posterior is still a tick too broad. However, compared to the coverage property obtained with ABC rejection sampling at delta equals 15, it was obvious that this is a massive improvement. Let us now summarize what we have seen today. Approximate Bayesian Computation, or in short ABC, is a collection of simulation-based methods for Bayesian inference. Because these methods rely on simulations rather than an evaluation of the full likelihood, they are suitable for models with intractable likelihoods. The most basic ABC algorithm is rejection sampling. This algorithm makes use of the two key approximations common to essentially all ABC methods. The first one is that the full data is replaced by some summary statistics. Using summary statistics instead of the full data allows for an easy way to calculate distances, but also usually results in a smaller space than when using the full data. This has a big impact on the acceptance rate. But despite this, it is usually not possible to wait for an exact match between the simulated summary statistics and those observed. Instead, parameter vectors have to be accepted just because they are close to the observed statistics. For this, some threshold delta has to be invoked. But despite these approximations, ABC rejection sampling does converge to the true posterior distribution if the chosen summary statistics are sufficient for the data, and if a threshold for accepting simulations is used that is very close to zero. In practice, however, it is almost impossible to choose delta so small as to get a very good approximation of the true posterior distribution. In fact, the delta is usually not up for choice, but it is determined by the available computational power. As a result, ABC posteriors tend to be too broad and to include parameter vectors under which it's actually impossible to obtain the observed data. This is where the ABC post-sampling adjustments come in. They aim at correcting for large tolerances delta used during the simulation process. The way they do this is they fit simple models to those ABC samples and use those models to improve posterior estimates. This is justifiable because, as we have seen today, the truncated posterior distribution, that is the posterior distribution obtained with the truncated likelihood and truncated prior, actually matches the true posterior distribution obtained under the full model. In practice, of course, neither the truncated likelihood nor the truncated prior is known, but the goal is to actually estimate those from the data. This might work well, simply because the truncated likelihood might be of a much simpler form than the full likelihood, as it only explains the relationship between parameters and statistics closely around S observed. Today I introduced the ABC-GLM method, a post-sampling adjustment that for instance just assumes local linearity around S observed. As we have seen in the case of inferring the allele frequency from genotypes, this assumption may hold really well. The reason is again that locally just around S observed, even a very complicated function might actually turn out to be linear. We have finally seen that any ABC inference should be properly validated. This is because ABC methods make tough assumptions, such as that the chosen summary statistics are near sufficient for the data and that the threshold for accepting simulations delta is small enough. In case of post-sampling adjustments, additional assumptions come in. For instance, in the case of ABC-GLM, the assumption is that locally around S observed, the relationship between the parameters and statistics is well governed by a general linear model. An easy way to validate ABC methods is via the so-called coverage property. The coverage property assesses whether the ABC posterior is a valid posterior. It does so by checking the position of the true value within the posterior distribution. If the posterior distributions are proper posterior distributions, then the true value should be distributed exactly as given by those posterior distribution. The coverage property assesses that by simply plotting the distribution of the position of the true values in the cumulative posterior distribution, which should be uniform if the posterior distribution is accurate. What makes the coverage property so easy to use is that the only thing required is actually to be able to conduct simulations under the model. However, we could not use ABC if that wasn't the case.